So in the last classes, we tried to look at this kinematics, especially deformation rate. And we try to define this deformation rate as half of del U plus del U transpose, one of the building blocks of understanding fluid mechanics. So we try to understand that there is something named trace of this deformation gradient tensor or deformation rate tensor, uh, half of del U plus del U transpose, that is this one. If I'm going to look at trace of these elements is del U1 by del X1 plus del U2 by del X2 plus del U3 by del X3. If I'm going to really look at that, that really tells me total linear. The individual components, I can always calculate del U1 by del X1 plus del U2 by del X2 plus del U3 by del X3. So basically, if I would like to really say, this is what you call velocity gradient tensor in fluid mechanics, del U. If I am going to decompose into symmetric parts and anti-symmetric parts, we will be going to get the individual building blocks of the system. One, what we call strain rate tensors, other one, what we call rotation rate tensor. So this is strain rate tensor and this is rotation rate tensor. In the strain rate tensor, we can really look at individual components, something like only on the diagonal, to understand volumetrically how it is expanding, compressing, and angularly how it is getting stretched, strained, and so on, so kind of things. We will understanding it from crosswise components. The pure rotational components, we will learn it from this rotation rate tensor. These are the basic concepts which we require it to begin anything. And last class also we have seen, if I would like to really understand the total angle made by this infinitesimal element, I will always be going to see del V by del X, the crosswise components, plus del U by del Y as the total change in angle between two of these axes. Now, what we are going to learn is something named principal strain rate and directions. For that purpose, first I need to understand whether you heard anything about eigenvalues in this system. I understand because you take something like a vector A, there is an operator A matrix maybe. You are trying to rotate it in such a way that the vector X, you finally end up with a vector which is scaled up. That means I take something like a vector, I'm going to transform, rotate it in three-dimensional kind of planes. I can rotate it in that way, rotate it in that way, rotate it in that way, and so on. So that such kind of rotation, if I am going to do that, it's not just one rotation, it might be multiple rotations or multi-directional rotations, such that I will end up with the same vector, but it is shrunk or it will be expanded. That's perfectly fine. But any other meaning associated with that? Hello? No? Okay, so let us think of a situation. Maybe there is a rope which is connected at two ends. It's a tightly stretched string. It might be your veena, sitar, or perhaps maybe other string kind of instrument. It can be even violin. You attach to 2 points very tightly. You just tap it. You don't continuously tap it, but just give an instantaneous impulse. Now this string won't does random oscillations, but it does either in that form or it does one particular set or it does a very finite number of mode shapes it will show. Your eigenvalues actually represent which one of them really get activated, at least in terms of physics. You can think of that. I can have something like very nasty way this string can vibrate, but it doesn't do. It only set into one fundamental note or higher harmonics. Especially strings, this kind of systems, if we are going to really show that these eigenmodes or eigenvalues represents what kind of shape oscillation it does. Maybe you can even think of, you take a pendulum, connect it to another pendulum. You can set by giving an impulse to one of this pendulum. The pendulum start oscillating to and fro, very tiny thing. After a while, the second one also, because it is connected to this common ceiling, some part of energy vibration really transfer there and start self-inducing oscillations develop in this pendulum. This pendulum also start oscillating. If you supplied enough amount of energy as impulse to these pendulums, though initially how complicated the motion might be, finally they will set into only two kind of motions. Maybe both the pendulums move in that way, or both the pendulums move it in that way. Either in phase kind of oscillations or out phase kind of oscillations they will do. It will be going to show you only two particular modes, named these eigenvalues or eigenmodes shapes. This is the natural way of looking at the systems, and there are many other kind of things also. Like you take something like water in a beaker, start tapping it, it starts showing something like surface wave oscillations. These eigenmodes actually represents that particular kind of natural modes of oscillation. Why systems behave that? For that you have to learn something about matrix theory, like how these linear operators map it and so on, so kind of thing. Leaving apart that, what you said like at the first stage, maybe if you have something like a vector, you are going to rotate it, very loose word, operating on that, you will be going to get the same vector, but it is scaled up, either shrinked or expanded. Such kind of particular beautiful transformation, what we call this eigenvalues, which will be comes from your characteristic equation and so on. In the same way, if we are using for our fluid mechanics problems also, or even for your solid mechanics problems, let us think of a situation. Because solid mechanics, fluid mechanics go together. There's a reason we have to really pick such kind of examples. Let us take some piece of chalk. Did you ever try to twist a piece of chalk or perhaps try to pull it? Ever try such kind of thing in real life? Played with the slate and chalk? Hello?
Yes, sir.
So how it breaks? Ever thought about it? How easy it is to break it in this way, where F is going out of the chalk, and how easy it is to crush a piece of chalk by pushing towards each other, the F, or perhaps applying same force on the ends, maybe hold it on one side and try to twist it, or hold it on other side, oppositely apply the stalks, and so on, so kind of stuff. Which one is easy to break that piece of chalk?
Twisting.
Which one? Let us put
Twisting.
numbers like A, B, C, D, E, and F. Can you help me out?
D and E are nearly same.
Wonderful. So you are in a position to recognize B. What are the ones you say?
D and E.
D for Delhi, E
E
for
for
this elephant. Okay. What about F?
F has a force, means longitudinal force also there.
Precisely. So it is more complex kind of motions or forces we are applying. If I'm trying to apply A, it's supposed to try to extend it. If the molecules are not, the adhesive forces in between these chalk molecules are not good enough, it will really break at that point of thing and it will try to expand in that direction. Maybe you are trying to compress it, crush it. If you are going to overcome the intermolecular kind of forces and so on so stuff, perhaps all these two ends really reach towards each other. Maybe the C example, if we are going to take, applying that kind of forces, though you can really break it, but mostly it start rotating about its center of mass. The D example, the delay example is you are holding it on one side. There is a force what you are applying at one of the end, but there is a radius so that either you might be trying to bend it. That means you might be trying to really apply a force in this direction into the plane, and so on, so that you are going to apply such kind of torque. Try to break it. Perhaps it might really break at an inclination kind of thing. D and E are more or less equivalent. It's more like replacing the reaction force or perhaps supplying additional forces. They will be one and the same. And F is more complex thing. Can I really bring all these kind of things into one framework, though it looks like they are completely different? Can I really bring all these examples into one framework to talk about how the material really deforms, breaks, twists, or whatever that? Such kind of analysis, what we call principal strain rate analysis, or this eigen mode decomposition or eigenvalue analysis. So usually is nothing to deal with fluid mechanics, but generally in mechanics, we apply different forces at different places, different directions, and so on, so kind of stuff. It may not be obvious whether the material really withstand or deforms, breaks, or whatever happens. By just saying that my force is this much, my torque is this much, I may not be in a position to really get the predicative properties when it is going to fail. Because many combinations of things are happening. Can I really grab all those combinations? Suitable transformation, I can do that, so that I can really convert this entire example into one particular example like D. A, B, C, D, E, F, all these things together, I can really club under one framework to talk about material properties. Such kind of thing, what we call principal strain rate analysis or eigenvalue decomposition. Shortly, we will see. Let us look at that. Can you see my screen?
Yes, sir.
So the whole question is in which case the material deforms, more or less breaks, withstand. So that question inspired to them come up with a plausible way. That's what we call principal directions. Though on material, infinitesimal element or finite element, you apply different kind of torque, different kind of forces. Finally, all these things lead to are exceeding certain limit. If it is going to exceed certain limit, yes, it is going to get deformed. No, it is not going to get deformed, but it is going to get experience something named shear stress, or it is about to strain in that particular thing. Especially the word what they have reserved is a principal direction is the direction where you will not see any shear stress in that direction. It won't have any zero strain rate. That really indicates that such entire combination, I can really make it into A or B kind of framework. Visualizing A is much easier, visualizing B is very easy. If something like, if I'm going to pull it, whether it is getting extended or getting compressed, is quite easy to handle at experiment. You can easily measure it. But measuring something like twisted is not that easy, at least some 100, 150 years back. And because of that, they introduced this mathematical framework. Pick this one, transform it in such a way that, or the vague word is rotate it in such a way that it's not material you are rotating, but the forces, stresses, all these things you are going to rotate in such a way that, can you find a plane where shear stress is zero on that plane? So everything will be in the axial direction. If so, what kind of directions it will be experiencing? So in a very abstract way, for if I am going to really put, maybe there is a surface here. I might be applying normal stresses and also shear stresses. Can I really rotate the material such a way that the shear stress contribution compressed to zero and everything mapped onto normal stresses? Can you visualize that? What I'm trying to say? Sometime back in an abstract way, we try to say A is a matrix, there is a vector X. I'm going to really map it into certain directional planes such that everything compressed or squeezed along that particular direction. And that direction, what we are trying to visualize here in terms of forces. You take a surface, there might be different directional shear stresses, normal stresses are acting. It's two dimension. If I'm going to really talk in 3D, this is one, this is another one, this is another one on that surface. Can I really rotate my plane in such a way that I can really see zero shear, but everything mapped onto normal stress? So that my analysis becomes easy to say that yes, material is going to get stretched, material is going to get compressed, material is going to break. Mathematically, if we are going to show, the easiest way to write is Ax is equal to lambda Ix. To take care of lambdas as scalars, I is an identity matrix, X is your vector, X is your vectorial direction, the plane direction, and what is that rotation required on the plane, so that I will see only normal stresses but no shear stresses. So the theory goes in this way. If I would like to really estimate that, what I am supposed to do is take my strain rate tensor. The strain rate tensor, what we have seen is del U plus del U transpose half of that. These strains can be normal strains. These can be shear strains. That also we have seen, because the diagonal elements are linear strain components. Off diagonal elements are this angular strain components. So the system is so complex state where each and every element is present. That is what we call this A. Let us think of matrix here. Can I really rotate that matrix in such a way that I will be going to get only diagonal elements, but off diagonal elements naturally becomes zero? The meaning of is you pick your strain rate tensor E, rotate it in such a way to particular plane X bar, so that you will end up with lambda Ix. Lambda values are diagonal element, which is possible only strain rate minus lambda I multiplied by X is equal to 0. In that case, if it can be happen, lambdas are called principal values or eigenvalues, and the X direction, what we call principal direction, or eigenvector. Is that clear? Hello?
Yes, sir.
Wonderful. If that is clear, now it is very well established mathematical technique where your E11 minus lambda, E22 minus lambda, E33 minus lambda, take determinant of this entire system, and whatever the lambda values you can really figure it out. That really tells you principal values, principal directions. And we have already seen from our previous example, the strain rate tensor is half of del U plus del U transpose, half of del U plus del U transpose. So 6xy minus lambda, 4yz minus lambda, 2x square yz minus lambda, rest of the elements. So this entire thing, determinant is equal to 0. So one can really estimate what is the determinant value by simplification, and one will be ending up with lambda values. If you solve this cubic equation carefully using your calculator, we will end up with some 3.5, 1.19, 7.29. These are the eigenvalues. So it tells you your strain rate on that particular direction, how many times it can really get stretched. That means a complex state, what you are trying to apply, really transform into such a way that 3 times of that vectorial length tells you the strain rate. 1 time of that strain rate, I mean like the principal direction tells you the amount what it can really stretch in the other direction. The 7 times it can really stretch into the other direction. that kind of condensed information, how far it really gets stretched, straight away given by your eigenvalues. Once eigenvalues are known, what we can always do is you plug that number a minus 3.514 of I, plug it, and x, find out x values. That is the way we calculate eigenvectors. So first what we are trying to do is note down lambdas: 3.514, 1.19, 7.296. So what you can do is you can take the notes which I have already shared, again go through line by line so that you will be in a position to really check whether you are getting such kind of lambda values. Once lambda is done, what we have to solve is pick your a, already we know a, plug lambda value, one lambda at a time. So for each lambda corresponds to, we have one eigenvector. For 3.514, you have one eigenvector. For 1.19, you have another eigenvector. What you have to do is plug xy values, lambda value. Then it turns out to be some simple matrix multiplied by x1, x2, x3 is equal to 0, 0, 0 for a given a, that is for a given lambda value. You fix lambda, try to get that. Now, what are those x1, x2, x3 combinations? As a unit vector, one can really find it. That is what we call eigenvectors. So when I plug lambda value, I will be going to get 0.582 minus 0.736 minus 0.344. These are the values which satisfy that first relation. Any multiple of that, 5 times, 15 times, 25 times, 100, whatever, that also eigenplane direction. It is more like you have figured out the direction. Usually the vector we represent by unit vector. Now any vector, multiple of that also the direction. So don't worry about that number. Similarly, when you plug another lambda, you will get another eigenvector. These are the directions along which maximum deformation happens with zero shear stress. And this has very important property when we are going to learn about turbulence. Try to understand what it means turbulence, where these materials really get stretched, deformed, or interacting with each other. For that, we require this eigenmode analysis. For example, like even if you are looking at slide digression, even if you are looking at machine learning kind of courses, where you try to really look at these eigenvalues, singular value decomposition, SVD, has more important role in terms of identifying principal structures of the system. It's more like you would like to draw Raja's face. How abstract you can do. If you can do that kind of abstract picture in a very vague way, you can think of it as eigenmode of Raja. Most of the features, but in a very abstract way, you are going to capture. That means any information, if I put it in a loose way, such a big information, can you really identify essential information of the system? That's what you call eigenvalues or eigenvectors. Maybe your string is vibrating in a very complex way. What is the most dominant way it can really vibrate, oscillate? That's what you call eigenvalues, eigenmodes. And these eigenvalues, once you know that, eigenvectors, you can construct any later things. And it acts like a basis vectors or spans the basis. So do you had any idea about this basis vectors at your algebra course at maths? Hello? Heard anything about basis vectors?
Yes.
So in the same way, these eigenvalues work. Okay. So let us look at another example. There is a 2D flow field. U is equal to U of y I bar. These are math problems, so science part always be bit less. So it is in the I direction or X direction where velocity field is varying. That means if I am going to really plot X coordinate, Y coordinate, U of y in the I direction means I should plot only velocity vectors in the I direction. But it has a dependency in y. in an abstract way, if I am trying to talk about, maybe it might be having zero velocity, velocity changes, velocity increases, and velocity further decreases, velocity decreases. In a very abstract way, the entire function u of y I can represent at a given x location in that way. Now, if I would like to plot this kind of velocity field at some other location also, some other x location, because it doesn't have any dependency in x, though the velocity field is in x direction, it doesn't vary in x direction because x variable is missing. That means whatever I have really abstract way drawn, the same thing I should really repeat. This is the u field at different x location. And there is no y component of velocity. Only x component of velocity exists. That's the reason I have drawn velocity in that direction. Now, you have such a varying velocity field in the system. Now, what I would like to really know is there only normal strain but no shear strain in this entire system? You can think of flow, a breeze passing over a terrain. There is a topography, earth, breeze is coming, breeze is moving. Maybe if you are looking at that, on the earth, velocity is equal to 0. As you are going into deeper part of atmosphere, it is going to increase. But as you are reaching outer layers of atmosphere, because there are no air molecules and so on, velocity going to decrease, everything becomes 0. So you can think of such kind of abstract nature. U bar is equal to u of y I bar. Now, in this entire atmosphere, entire flow is happening only in one x direction. So if I'm going to calculate strain rate, because there is a velocity variation, there is something like shear happening if I move vertically direction. So as I am trying to look at in the vertical direction, everywhere I experience shear, because how u varies in the crosswise direction y represents certain components of strain rates. Now, is there a particular direction? Here I will be like, if something like a tree is placed, you can think of there is a tree is placed. Because of this wind, it will be really get strain, start experiencing shear in that direction because of this wind. But is there a particular direction where I won't see shear, but only normal strains? There is only normal strain, but no shear strain. Can I really find it? That means, can I really look at one particular plane where I experience only normal, but no shear? So natural choice for us is to really look at principal thing. So it is a two-dimensional world. So let us begin del u. Deformation rate tensor is half of del u plus del u transpose. The other components are 0, 0, 0, 0, 0 if I'm going to look at in 3D. Because there is no W component, whatever might be. So these components will be 0. In the same way, if I would like to really write just in 2D, del u1 by del x1, del u2 by del x2, and half of del u2 by del x1 plus del u1 by del x2, and repetition of that. So write that. What is del u1 by del x1, which is del u by del x. And we have already seen u is equal to u of y in the I direction. So del u by del x is 0, first component. Half of del u1 by del x2. That means how u varies with respect to y, half of del u by del y. Similarly, this one repeats, half of del u by del y. The third component is del u2 by del x2, that is del v by del y, that is 0. So we already know the main rotation matrix. This is A minus lambda ix tells me the information about eigenvectors as long as that A minus lambda I is equal to 0. So I can always calculate minus lambda half del u by del y half del u by del y minus lambda x1 x2 is equal to 0. So if I derive that, lambda square minus 1/4 del u by del y whole square is equal to 0. That means lambda is equal to half of del u by del y minus half of del u by del y. Let us just for easy sake call half of del u by del y as gamma dot, just for notation. So it is plus gamma dot or minus gamma dot. These are the lambda values. Once I have lambda values, I can always calculate eigenvector as 0 gamma dot 0 minus lambda I is 1 0 0 1 x1 x2 0 0. So minus lambda gamma dot minus lambda x1 x2 is equal to 0. So we have two equations. Can I really find out x1 x2? So the first equation is minus lambda x1 plus gamma dot x2 is equal to 0. If you plug x1 is equal to 1 by root 2, x2 is equal to 1 by root 2, it gets satisfied. Look at x1 is equal to 1 by root 2, x2 is equal to 1 by root 2, where lambda is equal to plus gamma dot. So this is the eigenvector direction. Similarly, if my lambda is equal to minus gamma dot, then I will end up with 1 by root 2 minus 1 by root 2. That means if I am going to really show the direction, x direction is I, y direction is z, and when I'm going to really look at the velocity thing, 0, velocity, 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 and velocity. Instead of moving either in I direction or Z direction, if I go along 1 by root 2, 1 by root 2 direction, or 1 by root 2 minus 1 by root 2, I won't really see any strain rate in the shear strain rate, but only I will see axial strain rate in that particular direction. Your shear always be 0 along that particular directions. So let us move on to a new topic named stream function velocity potential. In some sense, this becomes our basis for fluid dynamics concept. And it has very potential advantage in terms of computational fluid dynamics. This concept named stream function and velocity potential lines help us to solve complicated fluid phenomena over aeroplanes, objects, planetary flows, and so on so stuff. First of all, let us define something named velocity potential and stream function. In the last classes, we have seen velocity potential means for especially inviscid flows where del cross u becomes 0, vorticity is equal to 0. Then in that case, I can always write u is equal to gradient of phi. And stream function for incompressible kind of systems, any velocity component is del psi by del y crosswise, and v is equal to minus del psi by del x. This is also part of, in some sense, kinematics. What we are trying to look at is what might be the angle between constant stream function lines and velocity potential lines. Can I really find it? So for that purpose, what we are trying to do is, as a worked out example, if velocity potential line is constant, that means you represent phi is equal to constant. Something like phi x, y, z, comma t is equal to something like phi. That represent velocity potential is equal to constant. In the same way, stream function psi is equal to some constant d1. You can think of psi is x, y, z, comma t. Especially in 2 dimensions, it will be x, y, comma t is equal to some d1. You can think of psi of x comma y can be as abstract like 5x sine y multiplied by 2x square log y and so on, so kind of stuff. That if I am going to specify it in that way, it becomes specific example. But a generic kind of thing, stream function psi is equal to d1. Now what we are trying to prove is this phi and psi lines are always be orthogonal to each other. For that purpose, what we are trying to show, let us begin with velocity potential. Phi of xy is equal to c1. And what I am going to really look at is any function constant means the change in that function value along that particular line. Maybe this is that phi is equal to constant line C1 on the XY plane. Let us assume. Along the line, if I am going to move from any point to any point, what I will call is d phi. That value won't change along the line is equal to 0. If there are multiple lines, phi is equal to phi1, phi2, and so on. D phi means if I am going to move from one line to other line, how phi2 minus phi1 varies. That is what we call d phi. But if I am going to move along the same line, the d phi value is equal to 0 because phi is equal to constant on that line. So the complete derivative, let us pick it. The complete derivative d phi is equal to del phi by del x dx plus del phi by del y dy is equal to 0. Del phi by del x, already we know u is equal to grad phi. That means del phi by del x is u dx plus del phi by del y is v, dy is equal to 0. That means the dy by dx along phi is equal to constant C1 line have a value minus u by v. If this is your velocity potential line, the slope of that line on the plane of x-axis, y-axis represents dy by dx. Where we are calculating? We are calculating on the line phi is equal to C1. That value given by minus u by v. Similarly, look at stream function psi. Psi xy is equal to d1. So along the psi line, if I am going to calculate, d psi is equal to 0. The same argument. Now let us calculate complete derivative d psi, which is equal to 0 on that particular stream function line. Del psi by del x dx plus del psi by del y dy. Del psi by del x already we have seen minus v. So minus v dx. And del psi by del y is u dy. So if I am going to rearrange dy by dx on the line psi is equal to d1, it is v by u. That means on the xy plane, if I am going to draw with the two different colors, so if I am going to show, it can be any object, maybe your aerofoil. There are certain lines going along the object, which we call in some sense streamlines. Psi is equal to d1, psi is equal to d2, psi is equal to d3. Flow is coming in this direction, two-dimensional flow, and you are looking at flow over a wing. A specific example. The line which goes on this black line may be psi is equal to constant streamline, whose slope is dy by dx is equal to minus plus v by u. And there is another line named velocity potential lines, the red lines, where phi is equal to constant, and they will be orthogonal to each other. At phi and psi intersection, we cannot really define any slope. And these are the points in some sense are usually associated with stagnation points also. So this word also again becomes important in our fluid mechanics. Stagnation point means your velocity field becomes 0. Maybe you take a plate, blow air or liquid. Liquid comes, goes along that plate. Touch, completely brought to rest, and again takes a turn. And it has advantage in terms of measuring pressure. If you are seeing aeroplanes and other things, there always be on either right hand side, there is something like a kind of nose kind of object always be there. And that nose kind of thing, what we call pitot tube, to really measure what is the outside pressure, inside pressure, whether aeroplane is working fine or not. Whether you take fighter aircrafts or whether you take ordinary aircrafts, there always be something like a sharp, tiny kind of gun, but it's not gun, tiny one. And that is basically our pitot tube. Earlier days, when electronic measurements are not that strong, they used to have this mechanical thing. And that become integral part of these aeroplanes. Even in the present electronic age also, you will have that pitot tubes, because when electronic failures happens and so on, so kind of stuff, these pitot tubes help the pilots to really drive or steer it in a better way. And the whole principle lies on the stagnation point principle, where entire fluid really brought to rest. And the second thing, knowing about the streamlines, velocity potential lines, some classes I say like, you may not really employ your XY coordinates or perhaps cylindrical or spherical coordinates. Something like body fitted coordinates are required to accelerate your computations. And the stream function velocity potentials are the natural coordinate system for solving CFD problems, which always align with the body, which we may never thought about it. But from math, it naturally comes out that the specialized coordinate system where computational programs work so efficiently is on this stream function velocity potential coordinates, because they're orthogonal to each other, they fit the body. Is that fine, guys? Hello.
Yes, sir.
Wonderful. So one more example we are going to look at. Show that in a 2D incompressible and irrotational flow. Incompressible meaning by definition d rho by dt is equal to 0. The material derivative of the density is equal to 0. The fluid particle should not get compressed or squeezed. It can deform. If I can really deduce mathematical thing for incompressible, del dot u is equal to 0. This is also equivalent statement from the velocity field. Though we look like a fluid particle, its density should not change. It should not change its volume, but it can really deform. A sphere, if you are going to take it, whatever the volume it has, similar kind of volume supposed to have, even if I stretch that sphere. Such kind of systems, what we call incompressible system. The material density or volume should not change, d rho by dt, but that can be equivalent in terms of how fluid is moving from one location to other location based on spatial derivative del dot u is equal to 0 happens. It's a byproduct. Such kind of systems, what we call incompressible. Irrotational, that means you should not have any rotation for a fluid particle. That means your rotation rate tensor are supposed to be 0, and its principal components, what we have seen, the vorticity del cross u is equal to 0. If that happens, we will call irrotational systems. Usually inviscid, that means no viscous systems, behave more like irrotational, though they are completely different things, but they also behave like irrotational. The fundamental criteria for irrotational is at fluid particle level, you should not have any rotation. You should not possess any angular velocity. You should not possess any vorticity. If these two conditions holds, then psi and phi satisfies Laplace equation. And this has another advantage in terms of solving fluid mechanics problems on computer. So 2D irrotational flow. So irrotational means you can always write del cross u is equal to 0. That means we can always write it in terms of a scalar potential del phi. So u is equal to del phi by del x, v is equal to del phi by del y. And also it is incompressible. That means del dot u is equal to 0. So del by del x of u plus del by del y of v is equal to 0. That means del by del x of del phi by del x plus del by del y of del phi by del y, which is equal to del square phi, which is equal to 0. So Laplace equation naturally gets satisfied for your 2D incompressible irrotational flows. Similarly, let us begin with your stream function. Incompressible del dot u is equal to 0. That means u is equal to del psi by del y. V is equal to del psi by del y, and v is equal to del psi by del x. This is. So irrotational also, del cross u is equal to 0. That means del cross u I need to calculate. So del by del x, del by del y, del by del z, del psi by del y minus del psi by del x, 0. Simplify it. Minus del square psi by del x square minus del square psi by del y square is equal to 0. That means your del square psi is equal to 0. So both stream function and velocity potential satisfies Laplace equation as long as the flow is inviscid or irrotational and incompressible. And there are specific examples like if velocity field is u, v, and w, find velocity potential and stream function. Is very easy. U is equal to del phi by del x. So a of x plus y is equal to del phi by del x. Similarly, v component a of x minus y is equal to del phi by del y. And b is equal to b is del phi by del z. Three equations, integrate one after other. Phi is equal to x square by 2 plus axy plus f of yz. Phi is equal to axy minus ay square by 2 z of xz. Phi is equal to bz plus h of xy. In this, what are the things supposed to be common for each of the case? That we have to really pick as phi is equal to ax square by 2 plus a of xy minus ay square by 2 plus bz. So that this condition also holds, this condition also holds, and this condition also holds. Because it should have yz components, it should have xz components, it should have xy components. That means it can be ax square by 2 plus axy minus ay square by 2 plus bz plus any arbitrary constant. That works. Similarly, stream function you would like to solve is very easy. U is equal to del psi by del y, v is equal to minus del psi by del x. So u a of x plus y is equal to del psi by del y. So one can integrate it to get psi. Similarly, v is equal to a of x minus y. So integrate it to get your xy. Out of them, what is the common thing? That is the way one can really solve psi xy.